In this problem, we are given a lot of information right here. We are given a couple of formulas down here as well, and we are going to use them to solve the I transient, which is this part, the I steady state, which is this part, and then the I total, this part. The I total is the combination of these two equations, and the I transient is the first equation, while the I steady state is the second equation. So we're going to look at all of them, and we're just going to plug things into them. First, we're solving for our I transient. That is part A. We're going to set our IT equal to this formula here. And now we're just going to plug things in and see if there's anything that we don't know. First, we need to plug in our VM. If we look at all the equations and formulas given, our VM is given in this part right here. We know that our 75 is the Vmax for this equation. So we are going to have a negative 75 on top. And then below this, we are going to have, per the formula, a square root. We know our resistance. Our resistance is 400 ohms. So we're going to have 400, and per formula, it is squared, plus, and then inside of here, we want the omega. The omega is given in this equation. It is the 4,000. So we're having the 4,000 in here, times our inductance. Our inductance is this part right here, this L. So we're multiplying this by 75 times 10 to the negative cubed, because we need to convert it from millis into just henries. And this is it for this first part of our equation. We just have to close the parenthesis and make it a squared, and that's all under the same square root. Now this is all being multiplied by a cosine, and then inside of our cosine we have our phase angle. Now we know the phase angle is given in this formula, or this equation, and it's this negative 60 degrees. It's going to be negative 60 because it should be a plus, so it's obviously a negative. We're going to have a negative 60 in here. Now we're keeping it in degrees instead of radian because we also have this theta right here. And we know that theta is this equation, and theta is measured in degrees. So we're just going to combine these two since they're both in degrees. Now we are going to have a minus tangent of -1, and then put everything inside of here because we're just substituting in for our theta. First, we have our omega times our inductance. It's the same thing down here, so I'm just going to copy this part and paste it in here, because again, it is omega times inductance, and that is our omega times inductance. And this is all over the resistance, which we were given as 400 ohms. I'm going to omit units just for all of this because it's a lot simpler. We know that since it's I, it's going to be measured in amps, though. And this equation is specifically asking it for milliamps. So that's it for the cosine part. Now we're just closing those parentheses. Now we are going to look at the last part, which is this E right here. So we are multiplying all of this by E raised to the negative, and now we have our R and L in here. So we're going to have 400, this is our resistance R, over our inductance, which we know to be 75 times 10 to the negative cubed, and this is in millihenries. That's why we transform it to henries by multiplying it by 10 to the negative cubed, and this is being multiplied by t. We're given our t right here, 750 microseconds, and we know that a micro is 10 to the negative cubed, so when we multiply this, it's going to be 750 times 10 to the negative 6. And that is our entire equation. Now we have to carefully plug this into a scientific calculator, making sure to use degrees instead of radians because we measured it in degrees. We're going to get that our I of t is equal to approximately 3.286 times 10 to the negative 4th. And this is in amps. We want our answer in milliamps, so we need to convert this. We know that we have 1 milli over 10 to the negative cubed, so we can cancel out this, and we're going to have a -1 here. So this is just going to move over 1 to the left, and we're going to get that our answer is 3.29 milliamps. And that is the answer for the first part. Now we need to plug everything in for our I steady state. Our I steady state is this second part right here. That is our equation here. The first part is entirely the same, so I'm just going to say that our IS is equal to, and then copy this entire first part because again, it's the exact same formula. However, in our cosine, we have some differences in here. We also don't have a negative sign out front in our V of M, but everything else again is the same. So we have our cosine, and inside of it, we have our omega, which is we know to be 4,000, times t, which we know to be our time. So we're multiplying this by 750 by 10 to the negative 6, plus our phase angle. This is for phase, and we know our phase to be negative 60. So we're going to have a plus negative 60 degrees minus our theta. And we know our theta we found up here to be this tangent part. So we can just copy this entire tangent part and put it in this equation. Currently, this equation that we wrote out will not work. This part right here, specifically in our cosine. And that is because right here, we have this in degrees. We know that our theta is also measured in degrees. However, this part right here is currently in radians. It's not in degrees. So we need to convert that, or we need to convert our degrees before we start this problem. Since we already have 2 in degrees, I'm just going to convert this beginning part, which is not in degrees, to degrees. So I will move everything over this side, and to convert something to degrees, we are going to multiply the conversion, which here is degrees, so 180 degrees on top, and the pi on the bottom. Now we need to carefully plug all of this into a calculator. And after we do this, we are going to get that our I of s is equal to approximately 0.03879. And this is measured in amps. We again want our answer in milliamps, so we're going to multiply this by 1 milli over 10 to the negative cubed. In doing this, we're going to move our decimal 1, 2, 3 to the right. And then we're going to get that our I steady state is approximately 38.8 milliamps. Before we start solving for C, I made a mistake right here in writing out our I transient. It's not 3.29, in fact we said it right here. It's supposed to be 0.329. So the answer for I transient is approximately 0.329. I had the decimal place in the wrong spot. Now we can solve for C. We know that our I total is equal to our I transient plus our I steady state. We know our I transient to be 0.329, and we know our I steady state to be 38.8. And if we add these together, we're going to get that our I total is approximately 39 milliamps. And that's how you would go about solving this problem. If you want more introduction to circuit analysis or voltages, resistance, inductors, and currents, there's a playlist as well as notes that covers this entire coursework in the description below.